Okay, so we have this equation and we want to solve it. Now, the characteristic equation, I think your book calls it something else, and I'm going to try to remember what that is going to be r to the fourth minus 2r cubed plus r squared equals 0. And that factors into r squared times r squared minus 2 times r squared minus 2r plus 1 equals 0, which is then r squared times r minus 1 squared equals 0. So your you have r equals 0 multiplicity 2, r equals 1 multiplicity 2. Now, your r equals 0 of multiplicity 2 gives you e to the 0x, which is 1. And then because of the multiplicity, without going through all the rigmarole about the reduction of order and stuff, you know that if you have multiplicity 2, you multiply the solution by x. You should know why, but one way or another, we get this. And then you have e to the 2x, and that 2 is e to the 1x, e to the x, and x e to the x. And I think you have all that in your solution. Let's look back. You have your e to the x. You don't have an x e to the x. You have a C2 for this solution, but you don't have an x. So your characteristic solution, and again, I'm having trouble finding the right words. That's not the right word, but you understand what I mean, is going to be, and well, could be any, you do C1 times 1 plus C2x plus C3 e to the x plus C4x e to the x, e to the x. Okay? And then you have your solution that gives you the e to the x plus 1. And again, just using heuristics without going through all the rules, but you want to really think through all the rules and how they work. Your particular solution, try a e to the x plus b. Now, really, that's not going to work because e to the x is a solution to the characteristic equation. Okay, so I'm going to say, well, actually, that's not going to work. But if we then add, let's say, a c x e to the x, then it should. Except that we have an x e to the x here, and that matches this. So we're going to also add a dx squared e to the x. Okay, so we maybe need all of this. Let's see how it works out. Then I should probably start with the first derivative, but these derivatives are pretty straightforward. Well, no, they aren't, because you got all the product rules and stuff. So it's going to be a little bit of a mess. Okay, so my p prime is going to be a e to the x plus c e to the x plus cx e to the x plus 2dx e to the x plus dx squared e to the x. And then it gets to be even more fun as we go on, because we got to do 4 derivatives of this silly thing. Now I'm wondering, and I haven't actually encountered this recently, I'm wondering if we could do a change of variable so that instead of y, our variable becomes u, where u equals y double prime. We could still get a solution and then do 2 antiderivatives of the u that we get. So all I'm going to say about this is, I don't want to take the time to work through all this, but this is where you are. By the time you do 4 derivatives of this, it's going to get really long. Try u equal y double prime, and u particular equals a e to the x plus b plus cx e to the x plus dx squared e to the x. In other words, the same thing that we had up here. And see how that works out. Make sense?
I think so.
Yeah, give that a try, and we'll revisit it next time. I just don't want to take all the time to do this, because in the first place, I'm going to have to probably end just a little bit early today. My driver's license has been expired for 3 months shy of 3 days shy of 5 months. Don't know if I mentioned that, but with COVID and not wanting to get sick and infect my wife, I chose not to go to the DMV. So they're going to yell at me and stuff, but I'll probably get a license of some kind. And if they don't drag me off to Guantanamo or something, I'll see you for our next class a week from Tuesday. Okay, well, all that aside, that's like immediately after my next class. So there's some things I have to do just to make sure I'm prepared for the next class and don't have to run over. So I want to try to at least finish up a little early, but I don't want to hurry through it. The subject of the next section is annihilators. Now, I'm just going to give an example of a couple of annihilators. Okay. Derivative with respect to x annihilates y of x constant equal to 5, since the derivative with respect to x of 5 equals 0. Okay, well, that's almost a trivial example, but to get the notation, we say that let big D stand for derivative with respect to x, then D of the function 5 is 0. Okay, now, this annihilates any multiple of C of x, and implicitly C is going to stand here for a constant. The first derivative is going to give you C, another derivative gives you 0. And we could say that second derivative with respect to x, I need a second derivative with respect to x, we write as d squared and I'll even write out the fact that second derivative is this. D squared means derivative of x. And let me actually write it that way just to make it really clear. It's a derivative of x, it's cx, but this means the derivative of cx equals the derivative of c equals 0. Okay. So the definition of d squared is derivative of derivative. Okay. Now I'm going to stop using the d dx notation and just use the big D notation. D to the n of let's say d to the n plus 1 of a polynomial, okay, of degree n is 0 because n plus 1 derivatives of any power of n less than n plus 1 going to give you 0. And that should be obvious. Okay, so that takes care of polynomials. Whatever the polynomial is, it's annihilated by, if the degree of the polynomial is n, it's annihilated by the n plus 1 derivative, which we annotate d to the n plus 1. Okay. Now, another annihilator that's easy to understand is okay. Well, question is, what annihilates e to the x? Well, I'm not going to ask you, I'm not going to try to drag it out of you because it might not be totally obvious until you see it. And then it really does become obvious. Well, d minus 1 e to the x equals derivative of e to the x minus e to the x, which equals e to the x minus e to the x, which is 0. So That's really easy to understand. Okay, what about cosine of x? Well, we'll give it away. Okay, first place, and I'm not watching my board here, make sure I'm good. Okay, I think I am. Okay, this is going to be d squared of cosine x plus 1 times cosine of x. Second derivative of cosine of x, well, first derivative is negative sine of x, and the derivative of that is negative cosine of x. So second derivative of the cosine is the negative of the sine, negative of the cosine. And you probably remember that because it's really important, like when you're trying to solve the equation for simple harmonic motion. And you might think back to that a little bit because it's an important connection. Okay, well, those are a few examples of annihilators. So you get the idea of what an annihilator is. You still don't know why we're talking about it, but unless you have some advanced knowledge, and you might. So it's a fairly easy concept. Okay, we'll get to why this is important and how it's used. But let's look at just a couple more examples that build on the ones that we just saw. Okay, first of all, what's the annihilator of e to the kx? Well, d squared d minus k e to the kx equals k e to the kx, because the derivative of e to the kx is k e to the kx, then minus k e to the kx, which is 0. Okay, what about the sine of kx? Well, that's going to be d squared plus k squared. Now, is that clear? If not, I can break it down a little bit more.
Yeah, that's pretty good.
Yeah, it's pretty simple. I mean, just write it out. And your book gives practically the same examples. So I'm going through them kind of quickly. So already we've got a vocabulary of quite a few annihilators. Okay. Now I want to first of all take a look at the book to see what they're doing and how they progress. It's all pretty obvious, but let's just be careful here. Okay. What's the annihilator of e to the 3x minus cosine of 5x? Well, d minus 3 annihilates e to the 3x. Now I got k here, not x. Okay. And d squared plus 5 annihilates cosine of 5x. Well, you might think that then d minus 3 plus d squared plus 5 annihilates the whole thing. But that doesn't work because then you'd have to apply d minus 3 to the cosine of 5x. And d minus 3 does not annihilate cosine of 5x, nor does d squared plus 5 annihilate e to the 3x. But the product of these annihilators annihilates e to the 3x minus cosine 5x. So this is an important, but not totally intuitive until you work through it, not totally intuitive rule for annihilators. Okay, your book is going to go into more detail on it. But if we work this out, you see exactly why it applies. So we're going to go ahead and apply this to e to the 3x minus cosine of 5x. So and I'm even going to do the algebra of this thing. I don't know if I want to because it doesn't illustrate. So yeah, I'm going to do the d squared plus 5 first. Okay. Second derivative of e to the 3x is 9 e to the 3x. And then we're going to have plus 5 e to the 3x. First applying this to the e to the 3x term. And then we're going to have minus 25 cosine of 5x. And it's going to be plus 25. I wrote this down carelessly. It's d squared plus 25. Actually, it wasn't just careless. It was like I wasn't thinking at all. But it's 25. So this needs to be a 25. And now we're going to have 25 cosine of 5x minus 25 cosine of 5x. And now the cosine of 5x is annihilated. What we get with the e to the 3x is 14 e to the 3x. Okay? So this annihilates this, leaving us this to annihilate. Now, the point about this is just a multiple of this. It doesn't matter what derivatives you take here to annihilate whatever you've got over here. All those derivatives are just going to add up to a multiple of e to the 3x, because anytime you take any derivative of e to the 3x, you're going to get a multiple of e to the 3x. So d minus 3 times applied to 14 e to the 3x is 42 e to the 3x. You take the derivative of e to the 3x, you get 3 e to the 3x. 3 times 14 is 42. And then minus 3 times 14 e to the 3x, that's minus 42 e to the 3x. And that equals 0. So that shows you something about why the product of the annihilators works. Basically, the annihilator of cosine of 5x is not going to change the fact that you have some multiple of e to the 3x, and d minus 3 will annihilate any multiple of e to the 3x, any constant multiple of e to the 3x. And if we did it in the opposite order, I don't want to write it out, but if we did I'm skipping steps here, you can work them out as easily as I can, probably more easily because you're less careless. A d minus 3 on the cosine of 5x gives us what? And actually, this is instructive. This gives us sine of 5x minus 3 cosine of 5x. Well, if you remember what we said back here, I didn't actually say it. D squared plus 1 annihilates cosine. And the same thing would work if you had a sine here. Okay, you can work that out. It's very easy. Or over here. Okay, here's a sine of kx, and it's annihilated by d squared plus k squared. So point is, you can work out the details, but this annihilator works in the sine of 5x or cosine of 5x. This at least illustrates the fact that your book will state in clear terms that differential operators commute. Doesn't matter in what order you apply these differential operators. Also, you can do algebra with them just as if these were algebraic quantities. Okay. Okay, you multiply this out with the distributive law. D of a D is a D of a D squared is a D cubed. And then we have minus 3D squared. And then we have plus 25D minus 75. If I apply this to this linear combination of functions, it's going to work just as well as this does. And I recommend that you just take a couple of minutes because that's all it takes. Okay, this has the same effect as this does. So it's like you can do algebra with the things. And again, you understand that better if you actually work it out. Okay, now we still haven't gotten to what's important about these things. And there are other cases. What's the annihilator of x e to the kx. So what's the annihilator of x squared sine of kx? Not hard to work out. Your book is going to do it. Let me make sure I'm not lying to you. And I'm scanning here real quick because I'm working on memory rather than common sense. Yeah, okay, they do that. And I'll let you read that. Just halfway down through the section, they give you a set of annihilators that includes all the ones I've got here, and then like a power of x times each one of the exponential, the sine, and the cosine. Once you have that, you got a really pretty good toolkit because you're going to recognize that all the functions that we've listed here are ones where it's really easy to do undetermined coefficients. You just do linear combination of the appropriate functions and solve for your constants. And you did that in the preceding section. And you understand that because it's fresh. So what's the advantage of annihilators? And now I want to really be careful to follow the notation of the text. And as I've said, yeah, another important aspect of this that I didn't mention is if you have a linear operator in sort of polynomial form, obviously then if it can factor, you can factor it and apply it, okay? And that's important for what we're about to do. Okay. So now, we're going to annihilate the left-hand side of a differential equation. Okay, I'm claiming that this annihilates this. So, writing it out. Now, d squared is just like a double prime. Since it's a second derivative, d is just like a prime and so forth. So we're going to write this out like so. Doesn't look like this is going to work out. And I said something stupid up here. As well, operating on the idea that what a stupid thing I said was actually going to work. Okay, we can act on everything I said there stupid. Okay. Thinking ahead, not thinking clearly. Let's fix it. Okay. Connecting these with the wrong words. Okay, this ought to be obvious. It's what I should have written in the first place. Okay. And it's minus 3y. And often forget to write the y there because I'm thinking ahead to the characteristic equation. So watch me. Okay. I mean, keep an eye on me. Okay, so we have this and it's equal to this. Okay, and that's really pretty obvious. Since we can factor these operators, this operator factors into this. And this is the same as this. Since this is the same as this, and this is the same as this is the same as this. Okay, so again, wanting to watch the notation here. The title of this section is Undetermined Coefficients. So what we can do is if we have the differential equation, and let's say this is equal to e to the 5x plus x squared minus 3 cosine of x. May be more complex than I want to say, but okay. It tells us that y double prime plus 4y prime minus 3y is annihilated by whatever annihilates this. And what annihilates this, so I'm going to have an annihilator here and an annihilator here. The annihilator here is d minus 5 for the e to the 5x, d cubed annihilates the x squared, and d squared plus 1 annihilates the cosine of x, Didn't leave myself room, so I'm going to have to spill over here. Okay, so this all applies to this. Well, that means that, give myself a little more room, d minus 5 times d cubed times d squared plus 1 applied to this side has to annihilate this side. Okay, so if I apply the annihilator of my non-homogeneous part of this differential equation to both sides, both sides get annihilated, which means that this is equivalent to this. And that's equal to 0. So what does this tell us? Well, if y is annihilated by d plus 1, just trying to find out how to write this, d plus 1 annihilates what? E to the negative x. Okay, now if you get used to what annihilates what and how it works out, work out some of these, do the derivatives, it's fairly obvious. D minus 4, and I say d plus 1, y annihilates e to the x. D plus 1 annihilates e to the x, so that the solution is going to include a multiple of e to the negative x. And it also annihilates any multiple of e to the negative x. So we're going to call that C1 e to the negative x. D minus 4 annihilates C2 e to the 4x. D squared plus 1 annihilates put a constant in there, C3 cosine of x. D cubed annihilates C4 annihilates any polynomial of degree 2. And D minus 5 annihilates C7 e to the 5x. So y equal to linear combination of these is going to be general solution to this equation. So this is a solution to the equation. You see the solution to the left-hand side here. And that's going to just be the e to the, I wrote down an ignorant equation here. And this isn't now working out. I wanted the 3 here and the -4 here. But I'm still getting okay. My original equation should have had the 3 here and the 4 here. Again, careless. Now the equation factors the way I said it did. Okay, the differential operator factors into this. The way I had it written originally, it wasn't even correct. So I'm going to take just a second and write down the equation as it should have been, so I can say what I was about to say. Okay, this is the same as this. And in the equation, of course, I need to reverse my 3 and my 4. And you'd think that would mess up everything else I've done, but it doesn't, because we haven't used this stuff previously. Okay. So there we have it. Now what I was about to say works. Your characteristic equation is going to factor into y minus 4 or r minus 4 times r plus 1, giving you solutions r equals -1 and r equals 4. And right there we have them. So these are the solutions to the homogeneous equation. And the rest of this, for the appropriate values of the c's, is going to give you this. And you, of course, need to work that out. Complementary, that's the word. So I'm just looking at the example and seeing how they explain it so I can complement it, using the word complement. Okay, so we again then match up these coefficients so they work over here. Meaning we're going to need to apply the derivatives to these things and see how they work out. And I don't want to go through that. It's going to be a little messy. Take a little while, but let's just take, for example, our C3 cosine of X. How are we going to get C3? Well, take the second derivative of the cosine and 3 times the derivative and 4 times the function. And I need, okay, I was careless when I wrote this down. D squared plus 1 does annihilate this. Okay, when you have the annihilator, it's a second derivative. Okay, and the second derivative is going to always involve 2 independent constants, which I'll call here C3 hat and C3, because I want to keep these numbered the same and I don't want to use up C4 through C7. So we have this. Okay, so these two, when you apply the operator, should give you -3 cosine X. So I'm going to say then, for example, D squared plus 1 applied to this should give you your -3 cosine X. Now, why don't we worry about D cubed or D minus 5 or D minus 4 or D plus 1? It's because applying any of those to the cosine of X still gives you a multiple, a sum of multiples of the sine of X and the cosine of X. So the D squared plus 1 is still going to annihilate whatever you do. So what I'm saying is that if you reorder these, remember these things commute, you put the D squared plus 1 out in front and do all the rest of this to your C3 cosine X plus C3 hat sine X, it's still going to give you some linear combination of cosine of X and sine of X. And the D squared plus 1 then is still going to annihilate it. So you solve this for C3 and C3 hat. So I'm going to go ahead and do that. Okay, this equals what? It equals -C3 cosine of X minus C3 hat sine of X, applying the D squared to the cosine and the sine, plus Okay, well, this just shows that d squared plus 1 annihilates this combination. And it's the rest of this mess that you use to get C3 and C3 half. So the rest of all this is d cubed times d minus 5 times d minus 4 this applied to C3 times the cosine of x plus C3 half times the sine of x equals what? Well, we can expand this. And we're going to get d cubed times d minus 5 is d to the 4th minus 5d. D minus 4 times d plus 1 is d squared minus 3d okay. I'm just full of errors today. It's d minus 4 times d plus 1. So the minus 4 has become plus 4 minus 1. Plus 1 becomes minus 1. And over here, okay, the characteristic equation is going to have a d plus 4 in a d minus 1. Just checking to make sure it's consistent. Going to have to change these signs and this. Something's still wrong, but I'm gonna go on with this. Actually, I'm going to pause the video for just a second and reconcile this. Okay, sorting all that out, what I had here was correct. Had to write this out just to convince myself. And we've established that this annihilates these guys. So the rest of this is what gives us the cosine of x. Now, expanding these operators, we get this times this. So now we use the distributive law, we get a d to the 6th, and then a d to the 5th, and a minus 4 d to the 4th, and then a minus 5d squared minus 15d. And I'd have been a lot smarter and choose a simpler function here so we'd get quite as much, but just to show that it works. Well, d to the 6th times cosine x, applied to cosine x, d squared is going to reverse the sign. Another d squared is going to bring it back to where it was, and another one's going to change the sign again. So we're going to end up with minus 6 C3 And I'm just going to write out the coefficients of cosine x first. And then 3d to the fifth. D to the fifth is going to give you negative sine of x. So this is going to be, okay. I want to do the multiples cosine of x first. So I want to find the coefficients to give me cosine of x. So a d to the fifth is going to apply to sine of x. Okay. Two derivatives is going to give me negative sine of x. Two more is going to give me plus sine of x. And another derivative is going to give me plus sine of x. So we're going to get plus 3 c3 hat. Sorry, it's going to give me cosine of x. And you can work that out. D to the fifth sine of x is going to be cosine of x. Okay. D to the fourth cosine of x is going to be cosine of x. So we're going to have a negative 4 c3 here. And a d squared cosine of x is going to give me negative cosine of x. So 5d squared times c3 cosine of x is going to be negative of negative 5 cosine of c3 cosine of x. That's going to be plus 5 c3. And then minus 15 c3 half cosine of x. Now, out of necessity, I skipped a lot of steps there, but if you work this out, I think it comes out this way. And if not, you still get the idea. Then coefficients of sine of x, a d to the sixth sine of x gives you a negative sine of x. So we get negative 6 c3 half sine of x from this. And d to the fifth cosine of x, well, d to the fourth cosine of x gives you cosine of x. And another d gives you negative sine of x. We're going to get a negative 3c3. And then d to the fourth cosine of x is going to give you cosine of x. We're going to have a negative, d to the fourth sine of x is going to give you sine of x. So you're going to have c3 half. A d squared cosine sine of x is going to give you sine of x. Negative sine of x. And then a negative 15d applied to cosine of x is going to give you well, d of cosine of x is going to be sine of negative sine of x. We're going to get this, which makes me think well, you can think about why it happens, but we're going to get coefficient of 6 here. Your c3 hat goes to c3 and I think gives you negative 3. That should have a 4 on this one. Five here. I'm not sure I've got all these signs correct. You got to work it out. We get this so that you have two simultaneous equations. This mess is what's going to give you the cosine of x. So all this is going to be equal to right-hand side gives you negative 3 cosine of x. Well, so this equals negative 3 cosine of x. So that this has to be negative 3 cosine of x. Well, actually, this mess has to be negative 3, and this mess has to be equal to 0. The coefficient of sine x is 0. Coefficient of cosine x is -3. Now that example was more complicated than it should have been, but you follow the same procedure to get your other constants. You have two simultaneous equations here, this equal to -3, this equal to 0. You solve them simultaneously, somewhat of a mess, but turns out a lot of your coefficients align and some of them don't align. So for example, if you add these two equations, well, don't have time to do it. You're going to want to rearrange these equations so that maybe you have your C3s. Yeah, let's look at it. Okay. This equation becomes what? We've got -6C3 and -4C3 and -15C3. Oh, sorry. And I should have a C3 hat on one of these. Uh-oh. Okay, yeah, we skipped a power. Okay, so the even power should give us C3s and the odd powers should give us C3 hats. So this is right. Okay, we have -6, -4, +5. That gives us 5C3. And then 3C3 hat and -15 equals -3. You do all this and you get -3 and 15. You get 12C3. And on your C3 hats, you have -6 and 4 is -2 and 15 is, okay, something's wrong. Yeah, I'm looking, sorry, unable to focus my eyes. That should be 2C3. No, there's a C3. Yeah, and the 15 should be a C3, not a C3 hat. Okay, so there it's right. And then I have -6 C3 hat plus 4 is -2 and 5. There's a system of equations. We can solve for C2 and C3. And now we know for C3 and C3 hat, we know what the coefficients are here. The others are simpler than that. I illustrated that one. And I apologize for getting messed up with some of the arithmetic, but that's kind of your process. And you might wonder, what's the advantage of this after all this mess? Well, most of the time your equation's simpler than this, and you'll see by working out a few examples how this can be an advantage. And we'll talk about that next time after you've worked over the problems. Feel free to email me. And again, not sure how clear all this is. Just to say it again. This is the same as this, and that's obvious. This factors into this. Finally, I got it right. And of course, then this is the same as this. So our equation here is annihilated if we first apply and where did I do it? I know I did it. I didn't write it out as explicitly as I might have. This annihilates this. This doesn't annihilate this equation. But since this annihilates this, if we apply this to all this. It annihilates both sides. And then we can see from what is annihilated by d minus 1 and d plus 4 and d squared plus 1 and d cubed and d minus 5. We list those. And the product of those annihilators annihilates both sides of the equation so that the sum of the things that are annihilated by d minus 1, d plus 4, all these factors is going to be a solution of the equation. Then we just took these two terms, for example, and applied d squared plus 1 to them. And d squared plus 1 has to give us our -3 cosine of x, because that's the only thing gives us -3 cosine of x. And the rest is just the arithmetic that we kept screwing up over here. Comes down to these equations, which we can easily solve for C2, C3, and C3 hat. The polynomial terms are annihilated by d cubed. So we can write out d cubed of all this is going to have to equal our x squared. Okay, and that comes out pretty easily. And then the last thing is our e to the 5x, which is annihilated by the d minus 5, and comes out with the C7 e to the 5x. And it's going to be easy to figure out what C7 is. You've only got one equation to work out there. To do, for example, C7 e to the 5x, okay, that's annihilated by the d minus 5 of this whole sequence. So you would take all these operators, expand it, apply it to C7 e to the 5x, has to come out e to the 5x, and you get your C7. Okay. Well, hopefully that gives you enough to work on. Email me if you have questions. I do have to take off. Okay.
Okay.
Okay, well, sort that out. Look at the examples in your book. They're simpler, but they're on the same idea, and see how it works out. And I'll see you after the break, but I'll be around through the break, checking email fairly regularly if you have a question or anything. Okay.
Sounds
Have a
good.
good day.
You too.
Okay.
Bye.
Thanks, Richard.